Okay, so my name is Andrew Sutton. This is my second talk on metaprogramming. My first talk was on static reflection. This was supposed to have been a talk with one of my coworkers, Wyatt, but apparently when I submitted the abstract for the talk, I managed to leave him off. So he's probably happy at this point that he doesn't have to be on stage presenting this. So he gets the glory, I get to do the work. So this work is actually it has been a fairly long project. This goes back to some work with initially Microsoft and Herb Sutter on metaclasses. And so that project kind of spun up a whole bunch of work on static reflection and metaprogramming in order to kind of get to the point where we could actually do something with metaclasses. So this is sort of like the top half of that set of language features. I do have to start with this warning. This is not going to be in C++23. This will definitely not be in C++20. This might be in C++26. This is still a work in progress. There are definitely some placeholders that you're going to see, some warts, some inconsistent semantics, I'm sure. So just be aware of that as I present examples, please. Oh, and I do apologize in advance to any compiler engineers in the room if you guys have to implement this. Okay, so generative metaprogramming. Turns out I may have made that term up because I was trying to find a reasonable definition online before my talk, and I failed. So generative programming, so it's really just generative programming and metaprogramming. Generative metaprogramming is really this classification of tools or approaches we have for writing programs that consume programs and generate more programs, right? Like preprocessors are great generative metaprograms. So if you think about like Qt's meta object compiler, that's a preprocessor. It takes in a header file with some Qt specific declarations, generates some C++ code that fills it out, gives you properties, dispatch, stuff like that. Domain-specific languages, pretty popular also. I don't know if anybody's used Microsoft's IDL, MIDL. Show of hands, anybody still using Corba? Good. No hands, by the way. So for those tools, we actually have to have separate compilers. We have to have a different language. We have to compile that down into something that can be added into a C++ program. If these tools solve your problems for generative programming, that's great. You can safely ignore the rest of this talk. If you don't really like these tools because you know their downsides, which there are several, you might be interested in some of the things I'm talking about. One of the big problems with these things is that you always have to maintain them separately from the language and separately from your build, right? As soon as you build a preprocessor, you have to keep it in sync with C++, and every new version of C++ comes out, you have to update your preprocessor to handle new syntax, possibly understand new semantics. This can become kind of tedious. It's a non-zero effort. Even if you're building a DSL, you still have to maintain that language and that compiler. It's extra effort to do these things. Ideally, what we'd really like to do is have everything in the same language. Perhaps ideally. Not entirely sure. Metaprogramming, somebody actually asked me this question the other day, like, what is metaprogramming? And admittedly, it was kind of late at night and I was a little tired, and I stumbled around. I was like, I don't know. But this is an auspicious beginning. So the way that we really use template metaprogramming, I think, in the context of C++ is just to mean compile time programming. We use it to compute types and we use it to compute values. We have template metaprogramming, so we do things like with type traits, so you can add const, remove const, find the result of a function call. We have const expert metaprogramming, which is really purely just compile time evaluation. A lot of our uses of metaprogramming involve observations of things that are already in the program. Type traits, for example, we use heavily to optimize generic algorithms. These are pretty good things, right? So generative metaprogramming, I'm just going to say, is a form of metaprogramming, at least for C++, that emphasizes the generation of code. That's what I'm going to roll with for generative metaprogramming. That's my definition. Now, we have tools for generative metaprogramming already. We've had them for a long time. There's a bunch of them. You guys are probably familiar with a lot of these, except the last two. Macros. Who loves them? I heard a woohoo. All right, good. Macros are kind of a form of metaprogramming. They work. You can use them. They're pretty powerful. Templates. How many people use templates? Yay, good. All right, so everybody, we all know what those are for. Fold expressions. Show of hands, that's pretty good. Expansion statements. Did anybody actually see the proposals for these? This was template 4 or 4 ... at some point. So this was supposed to be for C++20, but we just missed the ship deadline on it, trying to word some of the semantics. It was close. And then C++23, we hope will get static reflection that adds some new features for this stuff. So I'm going to talk about these and the capabilities of them a little bit. All right, so macros, as far as generative programming goes, macros generate tokens. We can generate parts of, you can basically generate whatever you want, right? Hopefully it's conforming C++, but I think at times that doesn't even matter so much. If 0, right? So they're really powerful. They let us generate anything, parts of classes, parts of functions, parts of expressions. The downside about these is they're not actually C++. They are part of the preprocessor. They have no knowledge of what your program is or what it does. You can't use the preprocessor in a way that relies on whether a type is trivially copiable or not, right? That happens before any processing does. So it's powerful, but it does have some shortcomings for what we want. Templates, fantastic. This is the workhorse of all template metaprogramming. We write things generically, we provide template arguments, we stamp out new definitions. Right? Nothing confusing about this. Fold expressions, we use these to generate iterated binary operations. So we can take the conjunction of sequences of arguments. They're fantastic. If you happen to use variadic templates a lot, that's great. Fold expressions, nope, not fold expressions. Expansion statements are potentially really, really powerful. They take the body of, they kind of work like a for statement, except in a normal range-based for loop, except instead of iterating, you take the body of a loop and you just stamp it out or instantiate it for each element inside of that list. So for example, if I want to find the minimum argument, this is probably not a great example, but if I want to find the minimum argument of a sequence of arguments, minimum value of a sequence of arguments, we can actually decompose it this way, expand over a tuple, which would be conformed from the tail of that list, and then actually compute the minimum of each step, assuming they all have reasonably comparable types here. Static reflection, I would talk more about this if I could, but I already did that for an hour. So static reflection adds a number of small generative tools for you called reification operators. So reification operators operate on, or basically they accept reflections or reflection values. So if you observe properties of something, reflect something, like if I reflects per int, that gives me a reflection of the type int. And then if I reify that with the type name operator, I just get the type name int, right? So we can generate small terms, which turns out to be very powerful in context. Some of these will actually show up later in the talk. But as far as like a real generative tool, like these help, but they're not really that powerful in and of themselves. So what's missing? Well, it turns out we have a lot of patterns that sort of declarative patterns that we can't really factor out of our existing code easily. We can't factor out and encapsulate. So if you think about, take for example an iterator, right? We know that there are certain patterns in building iterators. There's a concept that defines them. You have to have these operators, right? Well, it would be great if we could actually minimize the set of things that we have to do or have to provide to implement an iterator and then just stamp out the remainder of those things, right? You guys have heard of boost iterator Façade? It's been a while since that's been popular, but those are the kinds of patterns that we'd like to be able to lift out of these things, encapsulate, and then inject back into programs later on. Basically, we're talking about generating parts of programs and adding them into our definitions later on, and doing so programmatically. All right. So generative programming is really based on essentially one large feature, which is source code injection, which of course turns out into two smaller features. We have to be able to describe the kinds of code that we want to inject. So we have to have some way of expressing what patterns we have, what parts of code we're going to generate. And then we actually have to have a mechanism that takes those parts and puts them into the program at some particular position. And of course, this doesn't really stand on its own. It actually builds directly on top of static reflection. We have to build on top of this. If we can't observe properties of the program, we're not going to get very far generating useful programs, right, at all. Like, we wouldn't be any better off than having a preprocessor system, essentially. Sure, you can generate code, but if you can't observe anything about the code that you're generating, this doesn't seem to be particularly useful. And of course, static reflection builds on top of context or metaprogramming and template metaprogramming. These are both kind of essential pillars for all the kind of compile time work that we want to do. So, the rest of the talk is examples. These examples are based on a compiler that implements these features. I've been working on it for 3 years now, 4 years? 4 years maybe. Wyatt, the other co-presenter, the absent co-presenter, has been working on this full-time for the last year, so he's pretty much the maintainer of this at this point. You can get it from GitLab in our repo. There's some documentation in the wiki along with some tutorial stuff. It's also available on Compiler Explorer, thank you, Matt. Although this might not be the most up-to-date version on Compiler Explorer. There was some late work yesterday, which I'll talk about. Sadly, these examples are not perfect. They may not compile as written. Wyatt and I actually did a fair bit of work yesterday to try to make sure that they were sane and that they would compile, although in the course of editing to fit things on slides, I may have made some mistakes. That happened on Monday also. So you can type along at home, or in the audience if you'd like. Just cross your fingers and hope the compiler doesn't crash on you. It shouldn't. If you duplicate exactly what I write, it probably shouldn't crash. All right, so first example. And I kind of have to apologize for the first example. I've been trying to find a really good hello world for template metaprogramming, or for generative metaprogramming, and it turns out to be really difficult to find an example that just introduces the basic concepts and solves a reasonably interesting problem. So, of course, the interesting problem that I'm going to solve involves bitfields, because everybody knows this. This actually ends up being a problem that I have to deal with on a fairly regular basis, and if you happen to work on Clang, then you're actually familiar with this problem. So inside of compilers, there's this tendency to take integer data associated with abstract syntax tree nodes and kind of compress that into the root node of a hierarchy. Integer data would be like booleans, small enum values, whatever. You just end up with like a 32 or 64-bit block of integer values in the base class of your hierarchy. And as you have derived classes, they might add more data. So we really want this kind of notion of an extensible bit field. We can add data as the derived classes work down. So this is a slightly difficult example, or more advanced than I'd like to present. So if I were working in Clang, for example, and not following Clang's coding conventions at all, because I like lowercase and underscores, my expression, like for my C++ expression, if I'm writing a C++ compiler, this is information that I would have for an expression in my tree. There's a value category. We have to know whether the expression is type dependent, whether it's value dependent, whether it has some unexpanded parameter packs, some other information besides, but these are kind of the obvious ones or the easy ones to talk about. Right. And then if I have like a derived class like a fold expression, I want to add a flag to say whether it goes left or right. And it would be great if I could actually just derive from that first bit field, set of bit fields. But this doesn't really work, right? For a couple of reasons. It is my belief, and hopefully somebody will tell me that I'm right, that the bits in this object are separate from the bits in the base class subobject. So instead of having a 32-bit integer for this class, now we have a instead of having a one byte object, now we have a 2-byte object, which kind of defeats the purpose. So it doesn't really work. And because it's inherited, we'd have to use a pointer or pass this thing around by reference anyway, so that's also not what we want. So there's a lot of reasons why we don't do this. So the way that Clang actually ends up solving this problem is just to redeclare the original set of bits, but kind of compact them into a field that's sort of unreachable, right? Like there were 6 bits in the original declaration, so we'll just put them there, and then you'll never use them. And then if you have a lot of these things, you just stick them into a union. And this thing goes into the base class of your hierarchy. So if you want your fold expression bits, you can just grab that field out of the union. If you want your common bits, you can just grab the common bits out of that union. And then you have some rules in your discriminators to make sure that you don't do the wrong thing. This is a reasonable solution. This is actually a fairly effective way to do this. I was quite pleased to learn this. But there are some downsides. It's kind of weird to maintain. You gotta, like, if you change the size of the common bits thing, you gotta update that everywhere, which admittedly is trivially solved with a const per variable, so it's not that big of a deal. But what I don't like about the approach is that if I have a fold expression bits object, I can't also access like the value category, whether it's type dependent, whether it's value. I can't access the things that I should have inherited, right? So one way we can do that is just to simply copy those fields out each time. And so if every class actually just duplicates all of these things, now in every one of these bit fields I can say, well, I have my fold bits, I can see all the original bits. It sort of looks like inheritance, or it feels like inheritance, even though there's no inheritance at all. And of course, this is also a maintenance problem because now you have to copy that stuff around, which you can, again, easily solve with a macro if you want. which may be how I did it on my own projects. But this is kind of what we want. So the question is, how do you do this generatively, or at least safely, with the language features that I'm talking about here? So the strategy for this implementation is actually fairly simple. It actually exactly matches what we would normally do with a macro. I want to put my common bits into that field right there. So now we have the problem of how do we declare them, and then what is the mechanism that actually injects those? And this is how we describe them. So this is, if you see the double underscore, that means the syntax has not yet been finished. So this is a fragment, or a class fragment. Actually, let me be precise here. This is the class fragment. So a fragment is essentially a part of a class. It's something that's going to be injected into a class later on. Actually, I shouldn't say the fragment isn't going to be injected. The things inside the fragment are going to be injected. So this is a class fragment is basically a sequence of member declarations that we're going to put into another class somewhere else. A fragment is an expression, which means an expression has a value. So the value of this thing is just its reflection. And all we're doing is we're getting the reflection value, the reflected value of that. Like this is very similar to the reflexbur operator. It gives you back a compile time value that represents these things. And we declare a context variable that holds on to that. So common bits is the value of that reflection. Injection is pretty easy. This is an injection declaration. It looks a little bit weird. It looks like an implication, but it's not. You guys will see where the syntax comes from in a second. So the injection declaration takes the fragment on the right, which is just an expression. As long as you have a reflection, you can inject something. And we'll open up the fragment and then replay all of those members, copying them into this class where that declaration appears in the program. And that copy, it's not really a copy. It's really close to template instantiation. Really what we're doing is we're kind of like sort of instantiating each member declaration into this class, performing a couple of substitutions, a couple of very important substitutions as we do that in order to adapt those declarations to the context where they're being injected, which isn't really very interesting in this example, but that's how it works. Right? So after injection, we get exactly what we should see, which is a sequence of all these declarations. So I get my fake inheritance-like version of bitfields, which are pseudo-extensible, I guess, and everything works out nicely. So this is actually fairly macro-like. I just want to point that out. One way to think of fragments is actually that they are somewhat like syntactic macros. It's just a blob of syntax, a blob of valid C++, that's important, that we are going to inject into a particular position in C++. So I'm going to come back and talk about this thing a little bit. This is not actually a magic declaration by itself. This is syntactic sugar. In fact, this actually boils down to this little bit of code right here. So this thing, this const eval block, this is called a metaprogram, or this is what I've been calling a metaprogram. This is a sequence of statements that are executed where they appear in the program. So as you parse this thing, you enter the const eval block, and you start executing statements. And the only thing that this const eval block actually executes is this statement, which is an injection statement. And this is the workforce of source code injection. This is how things actually work, how the declaration actually works. So just like before I said, we're going to open up the fragment and copy this in. That's not quite the whole story. Really what happens is that we open up the fragment, we start replaying those members, each of the members in the fragment. But each of those members actually ends up being a request to inject this code later. So we don't actually modify the program as this thing executes. All we're doing is queuing requests to inject code at a particular point in the future. In fact, here, at the end of the metaprogram. So anything that would generate code is only ever actually finalized, kind of like transactionally emitted, into your program at the end of the evaluation of this metaprogram. And the reason we did this was actually pretty important. If you, for example, if you have a loop, a compile time loop that is reflecting over all the members of your class, and you're injecting members into your class at the same time, your loop will not terminate. And I know this for a fact because the implementation used to do that. So we end up buffering all these things. So all of your injections happen at one point, and they're not visible. You can't observe that an injection happened until the metaprogram ends. Can we do after? Okay. All right, I mentioned facades before. They're making a comeback. Boost iterator facade. So a facade is essentially just a little tool for building classes that model concepts. Boost iterator facade is a great example of this. I think it's probably the first example that I'm familiar with. Implementing iterators is a pain. You have to provide like a dozen overloads. And there's really only 5 functions that all of those invoke. You can dereference them, you can increment them, you can compare them for equality. Those are the 3, for input iterators, those are the 3 essential functions. Everything else is derived from these 3 functions. So these iterator facades actually give us a tool for simplifying our implementations of more complex concepts. I was going to write this example to use equality comparison and like less than comparison, but it would have been a bit self-defeating because we have the spaceship operator in C++20. So we get iterator facades. So the boost iterator facade, by the way, is a base class. It's one of these curiously recurring templates. You derive from it. You provide as a template argument the class that you're defining, and then it builds out a bunch of declarations that are instantiated later on when you use them. So we're going to do something similar. So this is the declaration of my input iterator facade. Sadly, it broke the line on the slide, so I had to wrap it around. But it's the same idea we had before. The only real difference is that we've actually given this a name. It's pretty important sometimes that you have to be able to name these concepts, or sorry, not a concept, these fragments. Because sometimes you have member declarations that actually refer to them, right? Like you can't have a pointer to a node class, without being able to name that class. So we make the name available here. The name, the visibility of the name ends at the closing brace of the struct, so it's not like it's introducing this name beyond the scope of the fragment. So here's my definition of the decal type auto iterator, the dereferencing operator. Returns decal type auto, so it's deduced, and it returns this arrow deref. Now, if you guys look at this in the following slides closely, you'll notice that there is no declaration of deref inside of this fragment. That's because fragments are dependent. They actually depend on the context in which you insert them or inject them, right? So remember, a fragment is just a piece of code that is going to be injected somewhere. It actually depends entirely on the context where it's injected. So when we write this arrow deref, we're basically delaying the lookup of deref until the point that we inject it. This is basically a 2-phase lookup for templates. If this were a template and it had a dependent base, that's how you get deferred lookup for your base class in templates, right? Same principle. So then when we go to inject this thing, we instantiate this definition, then we'll do the lookup, the delayed lookup, and we'll find, hopefully, a dereferencing function that will actually make the function work. Incrementing, same idea. You can see that this arrow increment. Only thing interesting here is that we actually name the type itself. Effectively, what's going to happen when we inject this declaration into an actual iterator is that name will be replaced by the name of the iterator itself. The equality operators we can derive this way. Not particularly exciting at this point. Again, they self-reference this type. Using the facade is pretty trivial. We just use a injection declaration, const eval arrow input iterator facade, and you're done. Everything works out. Right. The injection in this case, and I want to point this out because this is one of the important substitutions that we apply. When you inject a class fragment into a class, we actually set up a substitution from the name of the fragment to the name of the class that you're instantiating into. So anywhere you use the name of that type inside of your fragment now becomes the type that you've injected this into. So anything that was, iterator facade, did I name that correctly? Yeah, sure. That's fine. Okay. I'm not insane. So anywhere we use the name iterator to refer to the type inside of that fragment will be replaced by list iterator in the enclosing class. And of course, anything that was associated through that dependent type will also be instantiated in kind of the same way, just like a template. So we end up generating code that looks like this, and I left off the equality operators because it would have pushed too much off the slide at the bottom of the slide. So you can actually see where the transformations have happened, except I forgot to change the operator star to a decal type auto. So that was my second injection, or second example. So getters, get functions. I'm leaving out setters. It's just redundant at this point. I don't write code this way, but I know that some people do, and some people really like getters and setters. So we give an example. right, so here's a book class. It has some properties, title, author, page count. By the way, this example actually evolved after my talk Monday because somebody asked if you could reflect on attributes. And I said, no, the implementation doesn't reflect on attributes yet. We haven't talked about it in evolution that much, in the committee that much. And so I was going to write this example up, but then I thought, if I just present this as is, then anytime I apply this metaprogram to transform thing, I'm going to generate getters for every single member variable. And that doesn't seem sane. You know what? Let's just go ahead and add the ability to reflect on attributes and see if we can get this done better. So that happens. This is the implementation change that might not be available on Compiler Explorer, because it was last night that it got pushed. All right, so yes, we do have a get attribute that will inform a metaprogram later on to generate code. The code in this case actually comes from this metaprogram. Notice there's no arrow in here, there's no injection statement. You don't have to have them directly in metaprograms. That's fantastic. They can just live in normal const expr functions, or const eval functions, I guess, excuse me. But so this function, gen getters, takes a reflection of the book. So essentially we're generating, that reflection gives you a view of the class and everything that's been declared in that class so far. And so we can actually observe those properties and figure out like what code we want to generate. And I will let you guys digest that while I take a sip of water. By the way, if you didn't see the talk on Monday, this will be very foreign. I did mention this built on static reflection, to be fair. Okay, so the function is actually fairly straightforward. We're just going to get the members of the class. The members of operator will give me the list of all of these members. Range-based for loop walks directly over those. If the member is a non-static data member and it has the attribute, and that's the new bit, then we're going to generate the getter function. Make sense? Not particularly complicated, which is good. This is worse. All right, so this is the gen getter function. There's a bunch of new stuff here. First of all, the injection statement actually just injects the fragment directly. You don't have to have it defined or declared anywhere. It's just a value. We can generate these values on the fly, so this works out nicely. Now, the thing inside of here, if you squint, you might be able to see that it declares a function. That is a member declarator, or it's a member declaration, sorry. The first line names the type, and the second name generates a name for a function. And I'm going to walk through these and explain this in a second. So, generating the type. So this is one of these static reflection operations, the reification operator. Type name is the reification operator. It takes a reflection of a type, and it generates a type name. So if the type of the member was int, this would generate the type int const ref, right? Okay. There's one small thing that needs to be observed here. That needs to be a constant expression. Because in order to generate code, you can only operate on constant expressions, right? Think of like templates. Template arguments must be constant expressions. You can't pass int x and then use that to instantiate an array, or the array template, right? And the reason I know that's not this isn't a constant expression because m is not a constant expression. It's a parameter. It's not a constant. So there's something weird going on here, right? Because this actually does work. And it turns out that we've made this decision that fragments they're kind of implicitly parameterized. So inside of a fragment, if a name refers to a local variable, what we really do is we actually kind of replace that name with like a constant expression placeholder. So if we come back here and look at the m in this case, that's not really the same m. That m inside of the type name operator actually refers to this invisible placeholder that we've declared as part of the fragment. And the reason we do that is because that actually makes this a constant expression, but also dependent, and it allows us to defer the meaning of that type name operator until some point in the future. Right? Because we do this, because we actually have these placeholders, when you think about the actual value of the fragment, like when you evaluate this thing at compile time, during constant expression evaluation, the value of a fragment is actually two things. It's not just the reflection of the class. It's also this mapping of the parameters those implicit parameters, those placeholders, to the values that we've just computed. So there's like a little contextual, almost like a closure that follows around this fragment that we're going to rely on later to generate code. So if you want to, like this by the way is really hard to work out the first time I implemented this, and I've always struggled to explain it, but there's really 3 things to look at here. So if you think about the way this works, we have to analyze the fragment during parsing, we see the fragment again during evaluation, and then we see the fragment again during source code injection, or at least the compiler sees it in the last case, right? So during parsing, what happens is when you get into the fragment, we actually go ahead and pre-identify all of our local variables and just set up placeholders for them. We just pre-declare them. So anything that was a local variable before, inside of the fragment is now going to be a constant expression placeholder. During evaluation, we actually create a mapping between those placeholders and the values that have the same names, the local variables that name them. During injection, so when we actually go to queue the injection from the injection statement, we just pass over that entire thing, the closure-ish thing plus the reflection. And then during injection, we actually set up additional substitution from those placeholders back to the parameters that they're mapped to. It's a fairly complicated process, but the results are kind of cool. And I'll show you what it looks like in a second. So the unqualified part, it also has one of these little placeholders in there. Unqualified is a reification operator. It's a weird one. It generates an identifier. Actually, it generates an unqualified identifier that has not yet been looked up. So the unqualified takes a sequence of things, usually strings and integers. So we actually generate, in this case, it's going to be get with an underscore followed by the name of whatever member it was. So if the member variable was title, this is get title. If the member variable was author, this is get author, and so forth and so on. And then the last thing, we return that because we can't actually save the name of an identifier. We don't have a mechanism for doing that. We have to keep repeating the unqualified ID construction so far. So we just use it again. You get the name of the member. So this would be, for the member variable author, it would be return author. And all of those names are going to be looked up and resolved when we inject this function. And actually, I might be lying about that a little bit. Let me see what's next. Okay, so yeah, this is what happens when you actually run the code. So if we had a string, a property called title with the attribute get, we're actually going to generate the code get title. Make sense? Okay. So, I'm trying to think if there's anything else that was interesting to say about this. Yes, I left something out. The reason that we actually have this process, and this is kind of fundamental. The reason that we have this process of setting these things up is specifically to defer the generation of code as long as possible. It turns out that we can't generate code during compile time evaluation because compile time evaluation generally has this principle that, or this rule that you can't have side effects. Generating code that modifies your program is a fairly heavy side effect of evaluation, right? So we need some way to actually bridge compile context per evaluation and code generation. And the only way that we can do this is to actually package up these values that we've computed along with code we want to generate and just defer that as long as possible, which happens to the ideal point happens to be at the end of the metaprogram where you inject it. Now, there is a little bit of an interesting thing here. This is actually injected in 2 parts. So we inject the declaration first, just to create, get title, and then imagine it being followed by a semicolon. And then at the end of the class, at the end of this class, we actually go back and inject the definition. We create the definition later. This is basically the same pattern that you have when you write a class to begin with. If you have an inline member function definition, you're allowed to refer to member variables that haven't been declared yet. That's because all of the analysis of the definition is deferred until the end of the class. I think the magic keywords here for this are complete class context. So we do the exact same thing with injection. It's almost like you were writing this by hand, which was kind of the goal, emulating these things. So this is my last example, which apparently this talk is a little bit shorter than I thought, but that's okay. Plenty of time for questions. Okay, so you guys know what existential types are? Some? Abstract data types? Type classes? Rust type traits? Okay, so abstract data type is, well, these are basically abstract data types. So conceptually, these are just a pair of an abstract interface and a concrete implementation. There's lots of ways these can get reified in C++. You can think of them as like abstract base classes and derived classes. That's not unreasonable. type traits, or like Rust traits, are kind of an example of these. Type classes are kind of an example of these. Lately in C++, we've gotten really fond of using any types or type erasure to generate these kinds of things. In fact, actually, an existential type is really a type erased. Like I think the purest expression of these is actually a type erased object. So I just want to point out that these slides are actually based on work that Cy Brand has done. There's a GitHub repo here. This is actually really interesting code. I found myself looking at it for about 2 hours this morning, trying to figure out what it did, and you should take a look. So these are the examples that Cy gives in his repository, but I'm actually going to talk about it a little bit. So I have this case. I have some producers. I have a static producer that just returns a constant value. Fantastic. Always the value 42. There's no reason for it to be anything else. And then I have a dynamic producer which just generates an increasing sequence of integer values. But the problem that I have is that I want a list of like a vector of both of these that intersperses static and dynamic producers. Right? Pretty common problem. There's a bunch of different ways you can solve it. For example, we could do this. We can generate an abstract base class, go and derive from that in each case, make a vector of unique pointers, shared pointers, do whatever you want here. Just, as usual, no naked pointers. That's bad C++. But I have problems with this. First of all, I might not actually own static and dynamic producer. I might not be able to modify that code. So this is already a non-starter. If it's in another library, I can't do this, right? You cannot inject base classes into somebody else's project. I mean, you could if you copied the project and then modified it, but that's not really the same thing. So beyond the ability to not modify these things, even if we did, this gets us into like reference semantics world. It's all 1990s style object-oriented programming. We lose this nice value semantic approach that we've kind of developed over the last decade or so in C++. So we don't really want to do that. There is a second approach. We could actually just jam these into a variant. That would also be a viable approach, but that would defeat the purpose of the next few slides. So we don't want to do that. The other solution, of course, since we've already talked about type erasure, is to go ahead and create a value semantic type erased object that manages an internal pointer to these things in the back end, and then sets these things up. Right, so this is what that program is going to, no. I would say this, that implementing type erasure by hand is hard. How many people have done this, like rolled their own type erased or value? It's tedious. You got to remember the pattern, and then you got to get the pattern right, and it's not a trivial amount of code, right? So of course, in a talk about generative metaprogramming, the only right solution here is, of course, just generate it all, right? Here's how we're going to do that. So this is the program that we have to generate this code. So this thing at the top I'm going to talk about a little bit, but that defines the existential type, as it were, or I think is the way that Cy calls it, a type class. And then we can just make a vector of those things, vector producers. We can emplace back static and dynamic, and this will just work. We can access these members you call produce. Everything just works out. It's perfectly fine, right? So this thing is a metaclass declaration. Actually, technically, the metaclass is just the existential, the name existential there. A metaclass is really nothing more than a metaprogram that consumes, basically it generates a new class from some existing prototype. So the producer class here, that's going to be the prototype. The existential metaclass, that's just a function that pulls that in and spits out a new class. In fact, the entire thing is really just syntactic sugar for this. Like, this is all the magic of metaclasses. They are not mysterious things. They build on only the things that we've talked about in the previous slides. So the way we do this is we take the initial class definition, that initial producer, and we stuff it into a hidden namespace. Just put it out of the way, put it out of your mind for a second. Then we're going to regenerate the producer class, because that's really what we're generating. And of course, we'll just keep a link to the original declaration around for convenience, because sometimes it's useful to see those things. It's useful to be able to write reflective queries or metaprograms against those at some point in the future, or even use them directly. And the rest of this is just a metaprogram, a const eval block, that calls existential, the metaprogram, and passes it a reflection of the class that you've just, of the prototype. That is the entirety of metaclasses. Right? And by the way, this design took a long time to figure out. I was really happy when the complexity of the original complexity of the metaclass idea was reduced to this code, because that means I don't have to do anything magic for them. All I have to do is some scope manipulation and then just drive through all of the facilities that we built. Remember that pyramid? Like all of that just builds on top of these. So this is like the easiest way to invoke this stuff that you can. It's fantastic. I really like this line of code here. So what does existential actually do? A couple of things. I'm actually not going to talk about the entire implementation. There's enough there that warrants its own talk, and I should not give that. I think it should be up to Cy to get up here for an hour and explain what he's done. Because there's some really interesting design choices there that I'd really like to ask questions about. So this is what existential does. It injects a class fragment. So this class fragment here that he's injecting, this is like the basic interface, the primary interface for managing the construction of your sort of inner object types, right? So we have this storage class that's actually going to maintain the kind of like an internal pointer to the concrete type that we're going to create. And then we have a constructor that's going to take an argument of that concrete type and just build it. That's how you build these things, right? Like that's the constructor that makes this code work. The in-place back stuff. Okay. And then after it injects all of that stuff, it just generates a bunch of calls to the forward. This generate call forwarders function is actually really interesting. It takes all of the operations in the prototype, of which there's only one in this case, produce, and it effectively sets up another call that'll call in through a sequence of objects in the inside. So it's just duplicating the same interface, but it's calling through to a bunch of internal structures. This is basically the storage class. I'm kind of eliding a bunch of code here. So the storage class sits on there's two interesting parts of this, or important parts. So it sits on a unique pointer to a model of the abstract type, and here the abstract type is the outer class, the actual outer class, not the prototype, but the one that we've just generated. So it sits on a model of that. And then in the constructor of this thing, again, we're forwarding in the object of the concrete type, and we're going to make a unique object of the derived class, which is an impl of the abstract type along with the concrete type. So model is going to end up being like the base class in a base class hierarchy, and impl of whatever is going to be the derived class. Make sense? Sure. And this is very vaguely what they look like. I'm not going to talk about the implementations, I'll just say what they do. So the model ends up being the base class in this hierarchy. It keeps around the type of the outer class, the actual prototype class. This model class actually has a bunch of metaprogramming in it that generates its own virtual table, which is cool. The implementation class, obviously it has the storage for the concrete object. So when you create the static producer or the dynamic producer, it's going to live in that object there. But it also fills out, again, it has a bunch of metaprogramming stuff that will actually go through and fill out the virtual table that the base class has created. It actually establishes function pointers so that when you call produce on the outermost object, that's going to work through the virtual table set up here and actually call the correct function on the class that you created in the back end. It's an incredibly interesting implementation, but it works, right? So we can push things back, and then we can actually grab the first producer out of there, call it. All this stuff runs through a series of generated virtual table calls, manually constructed virtual table calls, and it should, in fact, because we pushed back a static producer first, return the value 42. I think Cy deserves a lot of credit for this. This is a really interesting implementation. I'm so glad that it was out there. So round of applause for Cy. Plus, it let me burn 15 minutes of a talk, so this is great. Okay, so that's actually all that I have for this. I do have one small observation. I presented this slide at the end of my talk on static reflection. Because all of our, like when we talked about static reflection, every single example had essentially the same pattern. We have some runtime code that calls into a template that uses reflection. And all that reflection code calls into some const eval, like the meta library code, to get properties, compute values, whatever. And on the way back, those properties feed back into the template that are used in if const expr statements, template for statements, or expansion statements, instantiating other templates to actually generate that code. And then, of course, the generated code comes back to runtime and you get really fast, top of the line efficient. Good C++, right? But except for the few templates that we had in Cy's example, there weren't any templates in this example. Like the first 3 examples had no templates in them whatsoever, right? So there's definitely something different here. Basically, we're just using metaprograms as the replacement for templates in this case. The generative mechanism that we would normally have from templates, generating code, we can just replace with a metaprogram and injection statements, right? So our computation, so what happens now is that we have this runtime code. We don't instantiate the metaprogram. That should actually say evaluate. Apparently I needed to fix that. So you evaluate or execute a metaprogram, and all it does is just call into this construct with the metaprogramming library stuff. That's just all reflection and like regular code. There's nothing weird in there at all, I mean, except for the reflection stuff, which can be weird. And then all of that code just injects declarations, which all get buffered or deferred or queued up until the end of the metaprogram. And at the end of the metaprogram, that's when we generate the code that comes back and executes at runtime. So all of our generative metaprogramming facilities in C++, if we have reflection, if we have source code injection, we actually get the best of both worlds. We can pick and choose. We can generate code through templates. We can generate code through metaprograms. We can assemble things with generic programming, which we have pretty good ideas how to do. We have a fairly principled approach for generic programming these days, or at least you should. You know, the concepts are here. It should get better. Concepts. No bias. But we can do the same thing with metaprograms. We just haven't quite figured out what the principles behind this are, but we can give you the tools to do this. So you guys can go and figure them out for yourselves. Come back and tell us what works and what doesn't. So, just to finish up, language support for generic programming, this is definitely work in progress. If you ever see syntax spelled underscore underscore as a primary feature, know that there are future designs coming. In fact, we actually just started working on redesigning fragments in their entirety. We haven't started the implementation of it yet. We're still kind of kicking the tires on some rewrite ideas for how these are presented. So maybe I'll come back next year and tell you guys how they're different. I've also really only presented about 1/3 of the features in source code injection. It turns out that trying to give a full talk, or like trying to cover everything, every one of the features that we've actually implemented to support these features, would probably be a talk every day for the duration of CppCon. There is a lot here. Or we could just do a 2-hour talk and be like drinking from a fire hose, but I don't think that's very effective as far as talks go. So I'll come back next year, give you guys an update, I hope. And then if you guys have any feedback, suggestions, questions, ideas, use cases, criticisms you can keep to yourself, we'd be happy to hear them. So thanks for your time. If you guys have any questions, come on up.
On your Metaprogram, you say that you do the injection in the close brackets.
This?
Way at the beginning. Yeah, I think so you make a promise that you inject common bits over there, and then when you get to the close bracket, that's where you actually inject the common bits, right?
Yes, the common bits are injected there.
Yeah.
Yeah, and the metaprogram kind of disappears from the program. Like once you've executed, it's gone. Gone.
Is there a way to, suppose I'm doing more things in this const eval, is there a way to roll back what I did if there is some problem?
No. I actually meant to mention this on one of the slides about books. So the model that we have for injection is that it's kind of like putting a pen down on paper. Like there is a point where code gets injected and there is no other point where code gets injected for the most part. We have some features that generalize that a little bit, but you can't really go backwards. We thought about doing this. We thought about supporting features where you could just sort of like arbitrarily go back and throw code into namespaces that you're not in, and that seems deeply unprincipled. And we don't want to go back and certainly modify classes after they've been completed, because that would like essentially break stuff.
But I mean, you made a promise of injecting common bits over there. Suppose in the next line you discover that you cannot do that. Can you roll back before you close the?
No. Okay. I mean, it's like putting a pen on paper and actually writing out the declarations. So whatever code follows can't conflict with code that you've generated. Like I couldn't have extra declarations of like value category in this case, because we would have already declared that. There's no rewind on this.
Thank you. I'm really looking forward to this because right now we're using the macro injection way of doing things. So this will be great. One of my questions is as we get more and more complicated code generation and code insertion abilities, how do you debug that type of stuff and make sure you're not messing up?
I assume at some point, at some time, some company, possibly called Lock3 Software, may have a compiler that allows you to debug your compiler. So you need more tooling for this. And it may or may not be being worked on. It's being worked on.
Can you show a slide after this with the deref?
With what?
This arrow deref in the fragment.
Just tell me when to stop.
Next one. This one.
Yes.
So if to skip this arrow, it will be just return deref. And the deref is not known as local scope. So does this necessary, or it would find the deref name from this scope and from scope where is instantiated?
The echo in this room is terrible. I can't actually understand what you're asking. I'm sorry. Can you actually come up and ask so the echo doesn't? Like, I don't hear the echo. In fact, just lose the mic altogether. It's like I can't hear them from the mic. Just come up. Come up. No. Come up, please. In fact, everybody, no mic. I can't hear. This is good. Yes.
If we remove this arrow from here, just return deref. So name deref is not known to be native of this. Just try to find deref from this scope or from scope where this fragment is associated to.
If instead of writing, so the question was if you had written, for example, decal type this arrow deref, would that be valid? Oh, if you drop the this arrow, then name lookup the compiler will try to find deref, and you get an error. I mean, if you don't have an existing version of deref, you'll get an error. So you actually have to use the this arrow to defer lookup until the point of injection. And we actually have some features that help defer lookup until later, but I didn't introduce those in this talk. Reis.
Do you envision us needing the ability to inject code in places that are not a class scope, for example, namespace scope or function?
So the question is, do we envision the need to inject code into non-class scope like namespace scope, function scope, template parameter scope, normal parameter scope? And the answer is yes, there are injection contexts for all of those and fragments for all of those. I just didn't present them because these are the easier ones to start with.
Are these the easier ones to start with, or are these the more useful? I guess what I'm asking is injecting into a class the most useful thing?
Is injecting into a class the most useful thing? I believe so, but there are definitely use cases where you want to put things in a namespace also. Namespaces. Thanks.
In the event that I left out a closing curly brace inside my fragment, and then started injecting stuff, I'm guessing I have no problem injecting. And then same way as macros, I'd start to come up with some interesting errors that I'd have to rationalize where the failure in the fragment was.
Yeah, if you mistype your program. Yes, sorry. I was repeating the question. So the question was, if you mistype your program, you're going to get some nasty errors because you might end up with sequences of nested injections, which can be weird. How do you track them down? And the answer is carefully. So we actually have some facilities in our implementation that let you do compile time printing and compile time debugging of code at constant evaluation time. So you can print stuff out as you evaluate it. But it can be kind of weird to use because sometimes that's triggered by instantiation, and sometimes it's triggered by evaluation. And it's never really clear when that happens.
Rather than, or in this particular case, the fragment being an isolated area of completely enclosed valid syntax. Like if the fragment itself would be able to, in isolation, say that I must be able to be a standalone entity, or could I leave at the end of a fragment const eval, and then at the beginning of the next fragment, arrow, and then something else, and then have confusing code that I'm looking at the end, and then they have to get put together again? Or?
Yes, you can write confusing code. It's hard for me to see the kind of situation you're talking about, but we can talk about it offline. I'd like to see the examples. Yeah.
First of all, I would like to say that Mr. Compiler, who's happened to be sitting in the front row, has indicated that yes, the new version is online.
Oh, good.
So thank you, Mr. Compiler.
So just an announcement. Apparently, the version of this compiler supports attributes on Compiler Explorer. So yay! Thanks, Matt. Can you write recursive fragments? Yes, you can. That actually shows up in some of our more examples on the webpage, on our wiki, yeah.
How powerful is this code generation in the sense that could it replace some of the compiler built-in magic like lambda generation or coroutine generation?
How powerful is this feature? Can it replace compiler magic? You don't want that. Even if it could, I don't think you want that. The compiler is better at teasing out issues and errors than library code will be. And it will generate better code for you as a result. I think that one of the things that will happen, like if we adopt this feature, I strongly suspect that one of the things that this will be most used for is experimenting with new language features that will then be proposed for compilers to implement. So this will be the prototyping space for those, and then they'll end up getting formalized. I think that will happen.
Could this be used to generate archetypes?
Can generative metaprogramming be used to generate archetypes for concepts? And for those of you guys that don't know, an archetype is basically a model of a concept that has no attached semantics. If you instantiate a template with an archetype, you can use it to support definition checking, right? Yes. Hypothetically, that is a direction that could be looked at in the future. It would be interesting. We don't have the ability right now to reflect on statements or expressions, which you would need to be able to analyze to generate the declarations for your archetypes. But I suspect that this will be something that we look at in the not too distant future. Mm-hmm.
You said that you put a pen on the place.
Yes.
Is it possible, for instance, if you had an Iterator generator,
Mm-hmm.
Iterator Façade, right?
Mm-hmm.
Suppose I had a container Façade, and I want to have a free function that calls size on that container outside of the function.
Yes. So the question is, can you generate free functions while injecting into class scope? Yeah. And the answer is yes. We actually do have a feature that allows you to float some injections to the enclosing namespace specifically to support that application. But I didn't present it because, fire hose. All right, no other questions? Well, thank you very much. You guys enjoy the rest of the talk.